Let's take a look at a radiation problem in heat transfer. Here we have a CSP, concentrated solar plant, right here. And for those of you who don't know what this is, it's what you can see down here. These are a bunch of mirrors that catch the sun's radiation and they reflect it every single one of them, all up here to this bright area. This area is called the receiver, and this gets heated like crazy, super high temperatures, and this heat gets transferred down here, and then we have like a Rankine cycle, and it helps us generate electricity. Okay, so this receiver is the part that we're gonna be working on in this problem. Pause the video, read the problem, and let's get started. So first up, we're gonna need to find the thickness of this wall of the receiver. So let's take a look and write up an energy balance and figure out what kind of incoming and outgoing energies we have. So energy in minus energy out equals energy stored, but this is a steady state, so this part is 0, in equals out. Okay, so on the wall, from all the data that they gave us in that previous text, let's see. So we're going to take a control volume on the outside layer of this receiver wall. So this is the outside and this is the inside. We have the flux that all these heliostats reflect. They come and hit the receiver. So we have this one, which is given to be 80,000 watts per meter squared. Now we also have some radiation that we receive from the surrounding, which is at 300 Kelvin. Now the surface will have its own emittance, right? It'll have self-emittance, so that's what we see here. And we have convection on the outside and on the inside. And also, importantly, we will have some conduction going through this material. Okay, let's write up all this information that we have here. First, I just wrote it out here with words so we can have a better understanding. Energy in is the radiation from the heliostat and heliostats and the radiation from the surroundings. On the outside, we have the self-emitted radiation and the convection on the out, and these two working together on this side, the conduction and the internal convection. Okay, now let's put in some formulas. Here, every single one in the same order. You can see them matching up. Here, for the last one, in case you're confused about this one, go back and take a look at the thermal resistance chapter. This and this is basically written up in the same manner. This is the thermal resistance according to the wall because of conduction, and this one is the thermal resistance on this side because of this convection. Okay. On this page, the first line, same thing that we had on the previous page, just copied over. Okay, so the first, what we absorb from these heliostats, right? So we need to find this absorptivity. Here's the formula for it, and all these radiation, they are coming from the sun, which we will use as a black body. So its temperature 5800. We can break this up into two integrals, and it will give us these two. Now, how we find these F's? This F, the wavelength times the temperature. Wavelength, we have in the text of the problem, they break it down for us how is the absorptivity with respect to wavelengths. Under 3 micrometers, we have 0.9. Above 3 micrometers, we have 0.2 right here. This is what we gonna utilize here. So the wavelength, which will be the 3 times 5800, the temperature from the source of the radiation, which is the sun. This will give us 17,400 micrometer Kelvin. Now we're going to take this number and we're going to go to our textbooks or wherever you have a table for black body radiation. Okay, and here you can find the corresponding value for this. If you can't find it, then most likely you have to interpolate for it. But this is the value that we find for this. Now we're going to bring this back right here. So for the first one, the first absorptivity from here all the way to 3 is 0.9 times what we found right here, right? Because this corresponds from 0 to 3 micrometers. Plus the second one is this section, which has an absorptivity of 0.2 times, we're not gonna go and find another F for it, because from the beginning all the way to infinity, that would be equal to 1. So we just interested from this part going all the way to 1. So all we're gonna do is simply 1 minus the piece that we find right here. That's gonna give us the missing part. There you have it, 0.885 for alpha S, the absorptivity, the amount of energy that we will absorb from that 80,000 coming in from the heliostats. Same kind of process we're gonna do to find the emissivity here and the other absorptivity, which relates to the surrounding. For the emissivity, remember that we're gonna use the temperature of that surface, which they said it cannot be more than 1000. So that's what we're going for, 1000 Kelvin. Same process here, just like I described right here. Okay, and for this one, the surrounding, they told us it's 300 Kelvin. So that's the temperature that we're gonna rely on. Same process again, just like here and here. Good, now we have everything that we need, and L is our unknown. That's what we want to find. Let's plug everything back in. All the values are plugged in. This is the left hand side, right hand side, and after hand wrestling with a lot of algebra, we can squeeze L out to be 0.129 meters. Good. Now let's take a look at the second question. We have our CSP plant, and they want to know the efficiency of all this energy being transferred in versus the energy that's actually used in the inside in this heat transfer fluid. We would have some kind of fluid, right? Heat transfer fluid that would take all this heat that was given to it and bring it down to our Rankine cycle to make electricity. So that's what they're asking. What's the efficiency from all this energy, converting it to useful energy? So the flux that was sent in versus the flux that came from the heliostats. Write up all our formula. This is the flux corresponding to this one. We used it in our previous energy balance as well, so it shouldn't be anything new. And this is the 80,000. Plug in all the values and we can find efficiency of this receiver is 39.12%. Alright, thank you guys for watching. Please give a like to the video and subscribe, and have a great day.